everybody. Just want to welcome you to today's STEEP Let's Talk About PFAS webinar series. For those of you that are joining us via Zoom, if you are looking to have a live transcript, which is kind of like closed captioning, you could turn that on at the bottom of your screen. It says CC Live Transcript. If you don't want to see it, feel free to turn it off in that same location. We'll be taking questions and answers and comments through the Q&A function at the bottom of your screen. And at this time, I'll turn it over to Cheryl Osimo.
Thank you very much, Sarah. Good afternoon. I'd like to thank everyone for joining us today for our fourth webinar in the STEEP Let's Talk About PFAS series. In our previous webinars, we were joined by STEEP scientists and local officials to discuss drinking water quality, the health effects of PFAS, and what communities can do to reduce their exposures and protect the local environment. If you missed any of these webinars, you can find them on the STEEP web page at web.uri.edu/STEEP or on the Town of Barnstable's Channel 18 video on demand platform. My name is Cheryl Osimo. I'm the Executive Director of the Massachusetts Breast Cancer Coalition, one of STEEP's community engagement core partners, along with the Sierra Club Cape Cod group. I am also the Cape Coordinator for Silent Spring Institute. Launched in 2017, STEEP is a research program funded by the National Institute of Environmental Health Sciences. The program is led by Dr. Rainer Lohmann and the University of Rhode Island in collaboration with the Harvard T.H. Chan School of Public Health and Silent Spring Institute. On behalf of the STEEP team, I'd like to welcome you here today for this informative discussion on the contamination of PFAS in the environment. We're joined today by Dennis LeBlanc with the U.S. Geological Survey and Bridget Rule, a PhD candidate at Harvard John A. Paulson School of Engineering and Applied Scientists. Our presenters today are going to talk about recent efforts to track down harmful PFAS chemicals in the environment, including a new study in which researchers uncovered previously undetected PFAS in 6 watersheds on Cape Cod. Following these presentations, we'll hear an update on the STEEP private well study from the co-leads of the Community Engagement Corps, Dr. Laurel Shader and Allison Mccann. I want to thank STEEP for organizing this series and Town Manager Mark Ells and the Town of Barnstable here on Cape Cod for their continued partnership. And now I have the pleasure of introducing Mark Ells, Town Manager for the Town of Barnstable. Mark has worked for the Town of Barnstable for 31 years and is currently the Town Manager. He has also been an adjunct faculty member at Cape Cod Community College for 19 years in their Business Administration program. Mark serves on several regional and statewide committees ranging from environmental, human services, education, transportation issues. Mark holds a bachelor degree in engineering from Norwich University and an MBA and MPA from Western New England University. We're so pleased to have Mark join us today. And now I'll invite him to say a few words, please. Mark?
Thank you, Cheryl, and good afternoon and welcome, everyone. I want to thank you for joining us for this webinar, Let's Talk About PFAS, the case of the missing contaminants. That's actually a very intriguing title. On behalf of the Town of Barnstable, we welcome you and encourage you to listen and learn about these contaminants of concern. This series of webinars has greatly benefited our efforts to educate and inform our public on this important issue, and I want to thank the STEEP team for all that they're doing. These PFAS are a class of chemicals that are widely used in consumer products. These chemicals find their way into the environment and can ultimately impact us. And there's hundreds of communities across the country that have been affected by the presence of PFAS. It's no coincidence that Barnstable has partnered with the STEEP team and Silent Spring Institute for decades. Our shared core values that everyone should live in an environment that's safe and free from pollutants of concern is at the foundation of that relationship. Informational forums such as this webinar today are critical to our effort to better understand how these contaminants impact us and to better manage these issues. For those of you who are familiar with Barnstable, it's our mission to maintain a high quality of life for our residents and visitors, and our water resources are an essential part of that quality of life. I will note, though, that our drinking water in Hyannis is now free from PFAS contamination, resulting from prompt action by our community to take the necessary steps to ensure safe drinking water. And concern regarding these and other emerging contaminants still remains ever present, and we need your assistance to stop the use of these chemicals through your education and your active participation. So thank you for viewing, and Cheryl, I'll turn it back to you.
Thank you, Mark. We're appreciative of Mark's support of the STEEP Superfund Research Program and for the longtime support of the town of Barnstable, which has paved the way for us to be doing this work today. Now, I'd like to introduce our speakers this afternoon, Dennis LeBlanc and Bridget Rule. Dennis LeBlanc is a research hydrologist with the U.S. Geological Survey in Northborough, Mass. He is a project leader of the USGS Cape Cod Toxic Substances Hydrology Research Site, coordinates the USGS technical assistance to the groundwater cleanup at the Joint Base Cape Cod, and participates in USGS Cape Cod nitrogen initiatives in cooperation with the US EPA. Dennis received a BS in hydrology from the University of New Hampshire and an MS in civil and environmental engineering from MIT. He has joined the USGS in 1975, and since then has been involved in many studies of the groundwater resources of Cape Cod. Bridget Rule is a PhD candidate in environmental science and engineering at Harvard University and STEEP trainee advised by Dr. Elsie Sunderland. He received his BS in environmental engineering from University of Colorado Boulder and is concurrently seeking his MS in applied mathematics. His research focuses on PFAS contamination from AFFF use and is investigating both groundwater and surface water on Cape Cod. We are thrilled to have Dennis and Bridget joining us today to share their research on PFAS. We'll begin with presentations from both speakers. After the presentations, I will introduce the STEEP Community Engagement Core Leads, who will be providing an update on STEEP private well studies on Cape Cod. We have reserved time at the end for questions from the audience. We encourage you to use the Q&A feature in Zoom to submit your questions throughout the webinar. We may not be able to get to all of the questions, but we'll take all questions into consideration and we'll do our best to answer them in future webinars. Thank you, and I'll now turn it over to Dennis.
Great. Can you hear me okay?
Yes, we can.
And you can see the slide, I hope?
Yes.
Okay, great. Thank you very much for joining us today. When you get into the high altitude above Cape Cod or look at it on Google Earth, what strikes me is obviously that the Cape is an island, but also you see that the Cape is dotted by literally hundreds of beautiful lakes. And these lakes are a sign or a field evidence of the sole source aquifer, the fresh groundwater that is really one of Cape Cod's true gems. It's an amazing natural resource. And what I'd like to do in the next 10 minutes is give you a quick overview of that Cape Cod aquifer, the groundwater and surface water, which act together as your water supply. I'll talk about the hydrologic framework, the water table, how the lakes and rivers are connected to the aquifer, and then end up with a little bit of a mention about the groundwater watersheds, which are critical to Bridget's talk. If we take a slice, like slicing through a layered cake, and look at the Cape Cod aquifer, on the upper Cape, which is the large panel on the upper left, we see that the sands and gravels that make up Cape Cod sit on top of granitic bedrock down several hundred feet below sea level. In fact, the bedrock doesn't outcrop anywhere on Cape Cod. So the bedrock is the bottom boundary of the aquifer. The top boundary is the water table, which is the top of the saturated zone in the sediments where all the pores are filled with water. The only source of water to the aquifer is a recharge from precipitation that comes down, enters the aquifer at the water table, and then gradually flows off toward the coast. Where the land surface has depressions that intersect the water table, we have our streams and our glacial kettle lakes. On the Upper Cape, the lateral boundaries, or the side-to-side boundaries, are bounded by the saline groundwater, the salty groundwater under the ocean that is trying to push its way in, but is pushed back by the fresh groundwater flow toward the coast. That's our freshwater saltwater interface. The situation is slightly different on the Lower Cape. You see in the diagram in the lower right. On the Lower Cape, the land area is much smaller and the depths to bedrock are much greater. So there is actually salty groundwater underneath even the fresh water underneath the mainland, and the fresh water forms like a bubble floating in the salt water. I'd like to now turn our attention to the water table, which is this upper boundary. The water table, as I mentioned before, is the top of the saturated sediments where all the pores in between the sand grains are filled with water. And the freshwater, the aquifer is cut off from the mainland by the sea level Cape Cod Canal. So it really is a totally independent hydrologic system. We can map the water table by looking at the altitudes of the lakes, the lake levels, and also by the thousands of monitoring wells that have been drilled. And we can contour the altitude of the water table like topographers do when they contour the land surface. This is a contour map of the Cape Cod's water table. The water table forms 6 hydrologically separate flow lenses that are separated from each other by sea level or near sea level topographic lows, like the Cape Cod Canal and the Bass River between Barnstable and Yarmouth. These freshwater lenses are hydrologically independent and there's no exchange of water between them. And they've been given names, as you can see, indicated in red. And then groundwater flows from the interiors of these freshwater lenses toward the coast. We can see dramatic evidence of this radially outward flow from the interiors of the freshwater lenses toward discharge at the coast into rivers and lakes because of the, based on this map you see here, of the contaminant plumes at Joint Base Cape Cod that was made many years ago in 2007. You'll notice how the plumes are all oriented like spokes on a wheel emanating from the center, dramatically demonstrating this outward radial pattern of flow. The map today would look very different because these plume extents are significantly reduced because of the cleanup on the base. The groundwater flows at a rate of about 1 to 2 feet per day. So it's fairly slow, but given the small size of the Cape, most of the groundwater in the Cape has been in the aquifer less than about 50 years. We talk about these freshwater, surface waters and groundwaters on the Cape really being part of a single resource, a single system. Cape Cod streams like the Kuna, the Quashnet River you see on the on the left with this photograph, are basically drains to the groundwater system, and they're groundwater fed streams. Groundwater seepage along their length is what results in the flow in the streams. And because of this, most of the streams on the Cape gain flow as you go downstream toward their discharge at the coast. They're called gaining streams. Where does this water come from? Well, if we look at the landscape and we use groundwater models, we can demonstrate that there's an area that's over which recharge falls as precipitation, and that recharge ultimately discharges to the stream. This is a computer simulated contributing area or recharge area to the Kuna Messet River, and all the flow in this colored area, all the flow in the stream at the bottom of this colored area originates as recharge in over this colored area. And we refer to this as the groundwater watershed. We'll get back to that concept in a minute. The glacial kettle lakes are a little bit different. They are actually part of the groundwater system. In fact, hydrologists refer to them as groundwater flow-through lakes. Groundwater seeps on the upgradient side of the lake, or the side of the lake that faces toward the top of the middle of the mounds, mixes in the lake, passes through it, and then lake water seeps back into the aquifer on the downgradient side. So the lakes, just like the rivers, have a recharge area or a contributing area. This map shows the recharge areas to the lakes on the western part of the Cape, where recharge falling in these green areas seeps into the lake on their up gradient sides, and then the lake water seeps back into the area, into the aquifer on the down gradient side. And some of the lakes obviously are obviously directly spill into rivers as well, like the Mashpee River coming out of Mashpee Pond. So when we put these two concepts together, the lakes and the rivers, as well as the water table, and we use computer modeling, we can begin to develop the idea of groundwater watersheds. This is a computer simulated watershed for Pompanesett Bay, again, developed by using groundwater models. It's important to realize that the groundwater watersheds are not fixed in like topographic watersheds are, but they can change as you add or subtract water from the aquifer. For example, by adding a pumping well and moving the water away from the watershed. So these are not fixed in space, but are dynamic. In this watershed, all the water coming into Pompanesett Bay, if we could measure the total flow, it would equal the amount of recharge falling on this colored area. Some of the water in this lighter green discharges directly to Pompanesett Bay without going through a lake or river. The recharge areas to the streams are shown in orange, and that water, of course, goes into the streams and it goes directly to the bay. And the area in dark green is the area that recharges the lakes, and then that lake water either goes into the streams and goes to the bay or goes back in the groundwater and then ultimately discharges to the rivers of the bay. So you can see how they're fairly complicated in concept here. But the bottom line is that the total area here that you see colored is the total recharge area that is providing water to Pompanesett Bay. Bridger in his talk is going to be talking about 6 different watersheds. I've shown 3 of them here, the watersheds to the Childs and Quashnet, the Mashpee and the Santuit. And he will relate where there are AAA Pfas sources from firefighting at several of these watersheds. And this one here, in particular the Childs and the Quashnet, you see the 2 sources on Joint Base Cape Cod. The point I want to make in this slide is that in the case of, for example, the Childs and the Quashnet River, if you look over on the right-hand side, the watersheds are really a complex mixture of waters that discharge directly to the rivers, that discharge into the lakes, and then discharge back into the aquifer and discharge into the rivers, or go directly to the rivers from up gradient. And so when Bridger talks about water samples he's collecting from the various surface waters, that water is really a mixture from a variety of different paths that it's taken to get there. And that can be quite complicated. So those are a few concepts to help you understand Bridger's talk. And now I'd like to turn it over to Bridger. Thank you very much.
Thank you, Dennis. Let's see if I can present interview. Here we go. Okay. Thank you, everybody. I am going to talk today about research that I have done as part of my thesis as a STEEP trainee, looking at PFAS on Cape Cod, specifically in the surface waters that Dennis talked about. So to start off, I'll give a quick introduction to PFAS and some important history terms during this talk. PFAS are carbon and fluorine chemicals that have been produced entirely by humans. And they can be categorized in many different ways, but there are 2 important groupings that I will discuss in this presentation. The 2 being short chain PFAS, long chain PFAS, and terminal PFAS is precursor PFAS. So to start off, long chain PFAS, which you are probably familiar with, include the chemicals PFOS and PFOA, have 6 or more carbons that are attached to fluorines, while shorter chained PFAS contain fewer 6 carbons attached to fluorines. Terminal PFAS, such as the 2 that I've shown here, cannot degrade in the environment because they are incredibly stable. On the other hand, precursor PFAS, which have these additional carbons that are not bonded to fluorines, have the ability to be degraded by microbes or sunlight and will eventually produce terminal PFAS. There are many sources of PFAS on Cape Cod. Two important sources that have been identified in the past include firefighting and training using aqueous film forming foam, or AFFF, and wastewater treatment and septic systems. Ongoing research has identified many health effects associated with chronic exposure to PFAS, including liver and kidney disease, decreased effectiveness of vaccination in children, cancer, and high cholesterol and obesity. So to dive a little bit more into the differences between terminal and precursor PFAS, there are, as you may have heard, thousands of PFAS that have been produced, many of which are precursor compounds. Precursor compounds are used in greater amounts than terminal PFAS in many PFAS containing products. For example, in historical AFFF foams, about half the PFAS present are precursors, while in the new foams that are used today, greater than 99% of PFAS are precursors. The shift towards using more precursors is due in part to the increased attention about the negative health effects of terminal compounds. Unlike the terminal compounds, precursors are much harder to detect and therefore are infrequently monitored in the environment. Moreover, we don't have much information about the health effects of these compounds. So if they're hard to detect, how do we measure them? Without getting too much into the weeds of the technical and statistical details, we use a method that artificially transforms precursors into terminal compounds that can then be measured using the standard techniques that are commonly performed by the EPA and the EPA standard methods. We then use a statistical method, Bayesian inference, to reconstruct the original concentration based on the number of carbon fluorines that they have in them. I'm happy to answer any questions regarding this technique in the Q&A or by email. So to go on to the study goals, we aim to questions. First, can the PFAS from AFFF be distinguished from other sources in watersheds that, as Dennis mentioned, have complex flow paths and potentially many sources? And then second, how much organic fluorine on Cape Cod is accounted for by the standard testing protocols from the EPA, which captures, again, mostly terminal PFAS, and then by our additional ability to capture the precursors. So to give an overview of the sampling strategy, we collected 57 samples from rivers and ponds from August 2017 to July 2019. Watersheds, including the Child River, Quashnet River, Mashpee River, Santuit River, Marston Mills River. The Childs River, the Quashnet River, and Mill Creek have known firefighting foam use. On the other hand, the Mashpee, Santuit, and Marston Mills River do not have known firefighting foam use and were used as background locations. Samples, we analyzed both terminal and precursor PFAS, and in the Messet River, we further analyzed for additional organofluorine. So what did we find? We found that we could detect terminal PFAS and precursors in all samples. I want to start off by giving a note about the notation on the slide. I'm using this metric right here that you can see, PM, which stands for Precursor. The different concentration that people who are familiar with seeing PFAS concentrations may be familiar with. Typically, PFAS are reported in nanograms per liter or parts per trillion, but this requires knowing the exact mass of each PFAS that is measured. However, Using the precursors, we don't have the ability to have this information, and therefore we have to use a different metric for concentration. And in this case, we're using the molarity. For general reference, concentrations of PFAS in picomolar tend to be around 2 to 5 times greater than the concentration that is reported in parts per trillion. PFAS, including the terminal and pre-PFAS in watershed impacted by firefighting foam use, was 750 picomolar, which was 15 times greater than the concentrations that we found in the background watersheds, triple F source. The PFAS exceeded the Massachusetts contaminant level for drinking water in most samples from the areas impacted by AFFF, but in none of the samples from the background sites. The Messet standard is for PFAS, none of which are precursors. In total, precursors made up 20 to 30% PFAS on Cape Cod, indicating that the current regulations are not targeting or considering a substantial amount of PFAS that are currently present in. We used the tools, including hierarchical clustering and principal component analysis, to assess the signature of AFFF use on Cape Cod. In the plot, which is results from principal component analysis, we can see that each of the dots represents an individual sample, while the arrows represent PFAS. PFAS in the AFFF site, shown in blue, are statistically distinct from the background sites, which are shown red along the dimension, which shows that this is the primary separation in the data. In areas impacted by AFFF, PFAS profiles are dominated by chained PFAS, such as PFOS, PSS, and precursors with 6 perfluorinated carbons. In the background sites, PFAS profiles are dominated by PFAS, such as PFBS and PFBA, as well as 4 carbon precursors, including the PFAS that are found in historical products, as well as the PFAS that are found in the modern day consumer products. We get whether or not all organic fluorine that we were able to measure. Using the standard testing protocol by the EPA, which is shown in panel A, we found that the majority of organic fluorine in the Quashnet River could not be explained by our measurements. When we included precursor to that estimate, we were unable still to characterize all of the fluorine, and we found that 40 to 80% of the organic fluorine was unidentified in the Quashnet. At this point, you might be wondering, why didn't we measure other PFAS or other organic fluorine compounds? We chose the PFAS based on their presence in the AFFF firefighting foams. In these foams, using this exact same method, we were able to measure 100% of the organic fluorine. Therefore, we can surmise that the additional unknown organic fluorine that we have measured in the Quashnet River could not have originated from AFFF use and must come from different sources. So what are we doing now to further identify what could be contributing to the unknown organic fluorine that we observed in the Quashnet River? I show a diagram of the universe of organic fluorine chemicals. In the center is the terminal PFAS that the regulations and standard methods target. In the larger circle, we include PFAS as well. Finally, there's that include all organic fluorine chemicals. These include compounds that are called ultra short chain terminal PFAS that are very small and contain 1 to 2 carbons attached to fluorines, and they're commonly found in precipitation. We are also looking into fluorinated pharmaceuticals and agrochemicals, in the SSRIs used for antidepressants, as well as following up on a recent year report that showed PFAS contamination from aerial spraying of pesticides. These chemicals are not traditionally thought to be PFAS, but some have been shown in research to degrade into the ultra short chain terminal PFAS. So in summary, we found that PFAS were detected in all samples in the Cape Cod watersheds. Watersheds that were impacted by AFFF use have highest PFAS concentrations and exceed the Massachusetts drinking water guidelines, which again are for 6 compounds. We find that there is a clear AFFF profile in the data using statistical techniques, and that precursors make up 20 to 30% of PFAS that we found at most locations on Cape Cod. However, when we looked at the total universe of organic fluorine compounds, our measurements were not able to explain everything that was present, and there is still a large amount of unknown compounds that need to be identified. Thank you.
Thank you very much, Bridger and Dennis, for those really excellent presentations. We appreciate it. And now I'd like to introduce STEEP's Community Engagement Corps co-leads, Allison Mccann and Dr. Laurel Shader. Allison Mccann is the Cooperative Extension Water Quality Coordinator in the College of Environment and Life Sciences at the University of Rhode Island. She has over 30 years of experience developing and delivering local, regional, and national programs focused on water resource protection for a variety of audiences, the impact of which has been to affect behavior change to achieve public and environmental health protection. Laurel Shader has been a research scientist at Silent Spring Institute for over 10 years, where she focuses on PFAS chemicals and other unregulated contaminants in drinking water and exposures from consumer products, including fast food packaging. Dr. Shader's research aims to identify drinking water supplies that are impacted by emerging contaminants from septic systems and other sources, and to work with communities in identifying and addressing local drinking water contamination. I'll now turn it over to Allison and Laurel for an update on the STEEP private well study they are leading here on Cape Cod. Thank you.
Great. Thank you, Cheryl, for that introduction. And thank you, Dennis and Bridger, for your excellent presentations as well. I will be presenting our brief update on our STEEP private well testing program and an update on what's happening here in Massachusetts with respect to PFAS testing in public water supplies. Allison Mccann, who co-leads the Community Engagement Corps, is on the line as well and will be part of the panel discussion at the end. So one of the goals of our STEEP Community Engagement Corps is to evaluate the presence of PFAS in private wells on Cape Cod. About 20% of Cape residents are served by a private drinking water well, as opposed to a public drinking water supply. As Dennis mentioned, all Cape residents rely on the Groundwater Aquifer as their source of drinking water. What I'm showing in the map here in blue dots, these are the locations of private wells around Cape Cod. You can see that most towns have at least some private wells, but particularly on the outer Cape are the most dense areas served by private wells. Back in 2018, we collected samples from 101 private well owners all throughout the Cape. And the samples that we collected were tested for about 15 or 20 different PFAS chemicals. They were also tested for nitrate and boron. These are both markers of septic system impact, and it can provide us some clues about the extent to which discharges from septic systems might be a source for PFAS into private wells. We also tested the samples for several trace metals, including lead and copper, which can come from plumbing and can be a concern on the Cape because of the acidic groundwater. We had planned to go out last year, last spring or summer, to do our next round of sampling. Obviously, with the pandemic, that was put on hold. But we did want to let people know that we do plan to go out again this summer, and we're still accepting new people to enroll in the study. And I'll put up a link at the end if you have a private well and you'd be interested in taking part in the study. I wanted to acknowledge the other members of our study team. Again, Allison Mccann from University of Rhode Island is the other leader of the Community Engagement Corps, And these are our partners from Harvard, Silent Spring, and University of Rhode Island on the research side, and Massachusetts Breast Cancer Coalition as well. So we've presented on our initial findings previously, and some of our previous webinars have touched on this as well. So if you'd like more information about our first round of findings, you can find that on the STEEP website. But I wanted to remind you or let you know about what we found from our first round of sampling. So we tested again 101 wells. The good news was that no wells exceeded the current US EPA guideline. I saw a question come in the Q&A about what is the current EPA MCL. And the EPA does not currently have a federal drinking water standard. So right now, according to the Safe Drinking Water Act, there's no testing required for PFAS, and water supplies don't have to meet any certain standards. Some states, including Massachusetts, have taken stricter action. And actually just last October, Massachusetts passed a standard of 20 parts per trillion for the total amount of 6 PFAS. And that was something that Bridger had mentioned. That standard was not in effect when we had done our sampling, but looking back at our results, we did see that 3 out of our 101 wells were above that new standard. But the good news was that the vast majority of wells were below that standard. PFAS were detected in nearly half of the wells that we included in our study, and about a quarter of the wells had 2 or more different PFAS detected. The PFAS that we found included some that are like what we call legacy PFAS, like PFOS, PFOA. These are PFAS that are no longer manufactured in the US, but are still persistent in the environment. We also found newer alternative PFAS that are being used to replace the ones that have been phased out. We also wanted to evaluate the extent to which septic systems might be a source of PFAS. We did find that wells with higher levels of nitrate were more likely to have PFAS. This can be an indication that septic systems are one source of PFAS. As we've talked about in previous webinars, many consumer products contain PFAS. Actually, just last week, there was a new study that came out on PFAS in cosmetics. So it suggests that septic systems can be one source, but there can also be other sources of PFAS into groundwater in areas where there's also higher nitrate. I also wanted to let you know about a new resource that Massachusetts Department of Environmental Protection has. Because of the new standard that Massachusetts enacted last October, public water supplies are now doing testing for PFAS in their drinking water. And so if you're served by a public water supply, you can go to this website and you can find out about any testing that's been going on in your community. And I can put this, I think I can put this in the Q&A at the end as well, so you can click on that to learn about PFAS testing that's going on in your area. So just to wrap up here, I want to make sure that we have time for questions at the end. If you do have a private well on Cape Cod and you're interested in taking part in our study, we do plan to have another round of sampling this summer. So you can visit our website right here, web.uri.edu/steep/wellwater. Previously, our test protocols had included our study team coming to people's homes, but just with COVID and I know things are improving in many cases, but for this year, we will be changing that up a little bit, and we'll be providing kits to people and instructions so that participants can take the samples themselves, and then we'll have some convenient drop-off locations. So if you have any questions or you want to find out more, you can send an email to myself or to Allison. And I also wanted to let you know about the past webinars that we've had as part of the series. In case you're finding us for the first time, we've had 3 previous webinars about PFAS in drinking water, PFAS health effects, and PFAS in consumer products. So with that, I'm going to stop sharing my screen, and that wraps up the presentation part of this webinar. If you have any questions for any of the presenters, please type them into the Q&A. And if the other presenters want to turn their videos back on, we'll start going through the questions. I guess to start off, Dennis, there was a question I think that's good for you to answer. What was the specific groundwater model that was being used in the Kuna Messet map?
There have been a whole series of USGS models that have been updated over the years as software and computers become more powerful. So the Kuna Messet map was made pretty early on in our work. So it was one of our older published models. I would have to look up which one it was. but we currently have several models that cover all of the Cape, and we would probably redo that one now based on current conditions and current understanding, although the results would probably be similar. So I can't tell you exactly which one. I would have to go back and actually look at the date of that map and then look at what model we used.
Okay, great. Thanks for that. There's another question, maybe Dennis, you might be the best one to answer this as well. I recently participated in a joint-based Cape Cod cleanup team meeting. There was a presentation on PFAS monitoring in the groundwater on the northern 1,500 acres. You mentioned that this doesn't pose a threat to the Upper Cape Water Supply Reserve. How is that possible? Is that something that you'd be able to answer?
I didn't see that presentation, and I do know that they've looked for PFAS on the upper, all over the training area and Joint Base Cape Cod, and my impression was that the PFASs were pretty much limited to the area to the south where it's developed, but that would be something you'd want to refer to or check with the actual environmental programs on the base, because I just don't know the details.
Okay, great. Thanks for that. Bridger, we've got some specific questions here for you. One question came in about the graph that you had from the principal component analysis. So the 6.2 FTS and the other PFCAs appear to split the two regimes in the hierarchical assessment. Where do they originate?
So the primary sampling locations for the AFFF impacted areas were in the Quad and had a couple sampling locations, Bill Creek watershed that is stream of the Barnstable Academy. When we looked at other avenues data, we found that there was actually a distinct difference between the amount of fluorotelomere and 6.2 fluorotelomere that we found in the Barnstable County area, which was much higher, suggesting that there was a mixture of both the new and old foams used at that, likely due to the fact that that site was through the 2010s versus in the Quashnet River and Childs River, which is downstream of JBCC, only really old foams that were high in the legacy compounds were the most abundant. And that's because those area firefighting foams hasn't been used. The last time it was used was in 1997. And so none of the new products would have been used at that time.
Okay, great. Thanks for that answer. Another one for you, Bridger. Can you go into a little more detail on the statistical methods used for identifying non-AFFF and AFFF PFAS?
Sure. So we looked at two different statistical clustering techniques. One of them is the principal component analysis that I showed, which characterizes the variance through the eigenvectors of the covariance matrix, your data, and finds as in the covariance matrix where most of the data is clustering together. The other avenue that we explored that agreed with the principal component analysis was a hierarchical clustering technique that is near neighbor method, and that you don't give the data or the model any information about what the samples are, and it just finds connections between similar compositions of PFAS until you group all of the different categories.
Okay, great. Thanks for that answer. Allison, I thought maybe you could answer the next question. If I would like to use a household purification system for my home, will it work for removing PFAS or short and long chain PFAS both removed?
Yeah, so It'll depend on the contaminant, the type of PFAS, but the EPA has identified basically 4 different kinds of treatment systems, some of which are probably more effective or more reasonable to use for home use for treating PFAS. And that would include granular activated carbon, also powdered activated carbon. You can also use ion exchange or reverse osmosis. So 4 different kinds. The ideal thing to do would be to have the water tested, identify what the PFAS chemicals are, and then get a treatment system that would most effectively work on those chemicals. And if you have any other questions, you can, specific questions about your water test results and treatment technologies around that to help remediate, contacting either myself or Laurel, we can work with you to help you identify that. Great,
Thanks for that answer. We had another question about treatment, which I'll also hand over to you, Allison. The question is, today it was said that drinking water that is treated, carbon filtered, she assumed is PFAS free. Does that mean there are no precursors or terminal PFAS in the water?
Yeah, I'm not sure I know the answer to that question. Somebody else might be better at answering that. I don't know. Do you know, Laurel? I'm not quite sure about that.
Yeah, I mean, typically when we say something is PFAS free, it means it's free of the PFAS that we're testing for. So if I believe you're referring to what Town Manager Mark Ellis said about the water in Hyannis being PFAS free. So the EPA methods include about 25 different specific PFAS chemicals. Precursors aren't necessarily included in that, so there could be other PFAS still in the water.
I always, when I work with homeowners about water treatment, when they've identified an issue, I always suggest that once treatment is installed, to do follow-up testing to ensure that the treatment system is working as you're assuming, or is working as it was advertised to work. And that happens not only after installation of the system, but also as the years go by, to make sure that the treatment is working effectively and help to identify whether or not any maintenance needs to be done on the system.
Okay, great. Thank you, Allison. Bridger, I might turn this back over to you since you've been in the lab doing the actual analyses. There was a question about parts per trillion being kind of a new range of concentrations that we're now able to measure. The question is, how long have we been able to measure to the parts per trillion levels?
For PFAS, it's been decades that we've been able to measure at the parts per trillion level. Some of the original studies that raised concern that compounds like PFOS were all around the globe found really high concentrations in the parts per trillion levels in polar bears. And what parts per trillion means is if you're 1 part per trillion, that means it's 1 molecule in 1 trillion other molecules. And today, the detection limits for PFAS have decreased even further, and many labs can get, if you extract enough volume of your sample prior to the analysis, can get into the 1/100th of parts per trillion levels. So the analytical capabilities are quite amazing and can detect at really low levels.
Great, thanks for that answer, Bridger. And a question came in about typical concentration of PFAS in precipitation. I know there was just a study or a news story that came out about that. Bridger, do you have an answer to that question off the top of your head?
Yeah, I can briefly. Concentrations of PFAS in precipitation can be pretty variable and are something that have not been very well studied, but typically are highest in urban areas or around things like fluorochemical manufacturing facilities or incinerators. And oftentimes the PFAS that is the highest concentration in precipitation is an ultra short chained compound called trifluoroacetic acid, or TFA. And TFA is a breakdown product of both precursor PFAS, but also of the HCFCs, the refrigerant replacements in the atmosphere. And those can be in the thousands of parts per trillion. There are several studies in Europe that show really high concentrations of TFA in rainwater.
Okay, great. Thanks for that response. We got a question about the specific PFAS chemicals that we found in our private well study. And we did another webinar where we really delved into the details of that. So I'd encourage you to watch that webinar. But here's the summary that we have in our private well fact sheet. And you can see the PFAS that showed up most frequently. Some of these, like I said, are the legacy compounds. So PFOS, PFOA, PFHXS, and some of them are newer replacement compounds. So these are 5 of the 6 that are included in the new Massachusetts standard, and we actually have an updated version of this as well that includes PFDA, and that was not detected. The PFAS that we didn't find were mostly related to these, so other perfluorosulfonates and carboxylates. But for the person who asked this question, I'd encourage you to look at the fact sheet to get more information about the specific chemicals we tested for. And let's see, Allison, I might pass it back over to you. We have another question about removal technology. Don't reverse osmosis and ion exchange technologies concentrate the PFAS? Where does the concentrate go? Is it discharged to septic systems and then into groundwater?
Yeah, good question. Yes, there is a backwash that occurs that in both of those systems where in reference to ion exchange, it would be concentrated in the media as the water runs through the ion exchange treatment system, exchanging, in this case, based on the question, the PFAS chemicals for another substance. That media is also backwashed to clean it, if you will. And if you're on a septic system, then yes, that would go, that backwash water would go to your septic system. It's, part of one of the reasons also why in terms of our private well water study, looking at, because most private well owners are on septic systems. And so we were very interested in our private well, as part of our private well water study, to see if, in fact, septic systems can be a source of PFASs through treatment, backwash, as well as showering, consumer products, doing laundry, etc. So some of the treatment systems, yes, if they're going to be backwashed into the septic system, then they can concentrate in your septic system. It's a good question. And then septic systems are designed to transfer that wastewater out into your backyard. And Dennis did a great job of talking about the impact of land use on groundwater quality on Cape Cod based on the nature of its sand and gravel makeup.
Great, thanks for that answer, Allison. Got a few minutes left here, so we'll try to get through a couple more questions. Question came in, Chatham recently had one public drinking water well that tested high for PFAS under the new state standards. Where would this PFAS come from? And should towns expect that they could incur expensive cleanup as a result of new testing? So I'll take a first pass at this, and then I don't know if others might have a more specific answer about Chatham. I don't specifically know what the source of that detection was. I'd be happy to look into that. But about the cleanup or the remediation costs, certainly for water supplies that end up needing to treat for PFAS, it can be very expensive. The town of Barnstable has been kind of ahead of the curve. Their contamination was discovered earlier, and they've spent, I think the most recent number is something like $20 million on treating PFAS in the contaminated water. And there's also cleanup activities happening at the Fire Training Academy. So I think the situation is different for different water systems. In some cases, contaminated wells can be turned off. And so that PFAS contaminated water doesn't enter the distribution system. But especially during the summer with high demand, water supplies need every bit of water that they can pull. So the remediation of the water and the treatment is definitely very expensive. So I think that's one of the challenges with PFAS, and part of the new state standard also includes funding for testing and designing treatment. So thanks for that question. I know Cheryl's coming on here. There's a great question for us to end on, and maybe Cheryl, you'd want to weigh in on this too. Do you have any action items for us? What would you like the lay people in the audience to do? So I'll take a first pass, and then Cheryl, you can add your perspective as well. I think it's important for us to realize we're all part of the water cycle, and we all have an environmental fingerprint. So the products that we buy, the things that we use in our homes and in our surroundings can end up in the environment. These PFAS are forever chemicals, and so once we use them, they are around for a very long time. So there is a connection between what we do individually and our water quality. So I would recommend that you can watch our previous webinars and go to the STEEP website as well for tips for how you can reduce your reliance on PFAS. So I'll pass it back over to Cheryl to wind us down here.
I'd like to thank you so much, Dr. Laurel Shader and Bridger and Dennis and Allison Mccann. Unbelievable presentations. For those of you who are joining us for the first time, please stay tuned, because we'll be back with more information for you. If you haven't, as Laurel mentioned, watch the other webinars. Please go back, watch them. We can get together hopefully every couple of months and provide you with more upcoming information. And on behalf of the STEEP team, I'd like to thank you again for joining us today. Thank you to our speakers once again for all the great information and conversation. Many of our speakers, for sure, and people in the community have heard me say this over and over again. We're doing this for our children, our grandchildren, and future generation. This is not a job for them to do. We're deeply appreciative of the town of Barnstable for their support of this program, and to the STEEP Research, Translation, Core, and Community Engagement Core for continuing to share their knowledge and engage the community in this critically important issue. A recording of this webinar, once again, will be made available on the town of Barnstable's website, as well as the STEEP website. Unfortunately, we weren't able to get to all of the questions today, but our team has captured them all, and we will do our best to answer them in future webinars. As with this webinar, future webinars will support not only Cape Cod, but also affected communities nationwide by sharing information and offering solutions so that communities can better protect themselves. Thank you, everyone, and have a good afternoon.